What is the geometric meaning of a differential equation, of an equation like the derivative of y with respect to x is equal to some function in terms of x and y? And we're going to see that these geometric concepts that we're going to introduce in this video are all parallel to what I'll call analytic concepts that we've introduced earlier in our differential equations playlist. For example, we've talked about having a solution to a differential equation, which is just some actual function that you take the derivative of and plug it into the equation and see that it satisfies. And so all of those concepts are going to have these geometric parallels. So let's begin. I have my differential equation, y prime is equal to f of xy. And the first thing I observe is that on the left, that is just the slope. The derivative we have geometrically interpreted all the way back in first year calculus as being the slope of the function y of x. So what this equation really does is at any point x and y, you can compute out f of x and y. And thus you know the slope at that particular point. As an example, consider the derivative equaling to just y. This is a differential equation we've seen previously. It's the exponential growth equation, and it has a solution. Y is a constant times e to the x. Plug that into both sides and it satisfies the equation. That's the analytic story. All right, so we're going to sketch something called either a slope field or sometimes a direction field. We're going to do this by hand first to build some intuition into the ideas. And then later in the video, we're going to see how we can get the computer to plot these and what that looks like. The idea is as follows. I want to imagine that I have the plot of x and y. So the x is my independent variable and y is my dependent variable. So what does it mean to say, for example, the derivative is equal to y? Well, let me imagine I have a point like perhaps this point right here. This is the point 1, 1. If I look at this equation, it says the derivative is just equal to y. So at 1, 1, it's saying the derivative is equal to 1. So I want to capture the notion that the slope, or that the derivative, is 1 here. And the way I'm going to do this is with a little line segment that has slope 1. As in, at any point, I put this little line segment, and that line segment has exactly the slope that the differential equation tells me. Now, note that because the right-hand side in this example actually didn't depend on x, any spot with y equal to 1 is going to have a similar little slope of 1 as well. So if I went over, for example, to here, where the x value is 2, but the y is 1, it would also have a slope of 1. And similarly, I can go and all the way along this curve, I'll draw a slope field or direction field where these little line segments all have slope 1. Okay, what about some other point? What about if y was equal to 0? That would be along the x-axis. Well, if y is 0, the derivative is 0, and so I'm going to plot little horizontal line segments all along this axis. That is when y is equal to 0. Similarly, if y was, how about y equal to -1? Now the slope derivative would be -1, so all the way down here, it would have slopes of -1 along that curve. And we can keep on doing this as much as we want. How about y equal to 2? Okay, that would be the derivative equal to 2. That would be even steeper, even more upright as I go along like this. And so what am I doing? At every point, because I can keep on going and doing this anywhere if I so wished, at any point, I draw a little line segment, and the little line segment tells me the slope. This kind of slope field is a way to encode a differential equation geometrically. The way I went about this was referred to as the method of isoclines. Okay, what is an isocline? Iso means same, cline is for inclination. So this is the same inclination, or in other words, the same slope. And what it is as a formula is saying that that right-hand side of the equation, the f of xy, is just equal to a constant. So here I've set the right-hand side to be 0 or 1 or -1 or 2. That is, these horizontal lines where the slope is constantly equal to some value along those lines, those are referred to as isoclines. And so these isoclines provide an easy way for me to plot at least relatively simple differential equations with a slope field. Okay, so now let's see a slightly better version of this by letting the computer doing the plotting for us. All right, so to help me plot this, I'm going to use a computer tool, and I'll put the link down to this in the description so you can put in whatever function you want. And I began with the derivative is equal to y, the same one that we started with. Now, what you see here is just a better version of what I already plotted. At any single point, you get the slope, and the slope is just determined by the y value because we have a simple right-hand side. But there's something I can do additionally here. You notice on the bottom here, there's an option that says Show Solution, And if I do that, well, I get this curve. So what's going on there? Notice how I have this red dot, and I can take that dot and I can move it around however I choose. This red dot is sort of like an initial condition. It's saying I want to start at some particular point, some x value and y value. And then it plots the curve, which says, do whatever the slope tells you to do. That is, this blue curve is sometimes called an integral curve. Integral curve is our fancy buzzword. And what it means here is that the slope of the integral curve is completely tangent to the slopes in the slope field. For example, if I just drag this down, how about all the way to the x-axis, where it's just going to be a horizontal line? Well, that makes sense because along the x-axis, the slope was 0. And so the slope of the integral curve and the slope of the slope field are the same. But I can move to any spot. Maybe I'll move up to this spot, which is 1, 0 here. You'll notice it exactly goes through the slope field at that particular point. But if it looks at all like it doesn't match perfectly, that's just an artifact of the fact that the computer is regularly spacing out the spots where it chooses to draw the direction field. But in the integral curve, it goes through whatever values it actually does, regardless of whether or not there's a slope there. But it does match at any single point. So if I go, for example, and move it up right there, it's going to match the slope at that particular point. So this is all sort of analogous to what we've seen in the past. There's an initial condition, that's that point, sort of where you start. There's sort of a solution, if you will, to the slope field, which is this integral curve, this curve that goes through that point, but is aligned with the slope field, has the same slope as the slope field at any given point. Let me do a slightly more complicated case. Okay, I've got y, I'll do y times x. Let's plot what that looks like. Kind of nice. And the same sort of story occurs. As I move where I begin, I get a bunch of different integral curves. If I go all the way down to the x-axis, in this case, it also, I can't quite get it aligned. Oh, if I go perfect, I think I could do it. There, I've done it, nice. If it's right on the x-axis, y is actually equal to 0, then the slope is 0. And then if it goes down here, it curls around as well. So this gives us the idea of a curve that solves, in some sense, the slope field because it moves through the slope field always being aligned with the slope field. Okay, so let's try to review everything that we've learned thus far. I begin with the first order differential equation. Y prime is some function of x and y. So firstly, on the analytic side, I actually have the ordinary differential equation. The description, the y prime is a function of x and y. And what we've seen is that geometrically, that corresponds to a slope field. So an equation is sort of the analytic viewpoint, and the slope field is sort of the geometric viewpoint. Okay, but then I could have, for example, an initial condition. So analytically, this is just specifying the y at some initial value x naught is just going to be y naught. So x naught and y naught are just constants here. So that's specifying an initial condition. Geometrically, what an initial condition looks like is you've specified some particular point on the actual slope field. And that's the spot where you're going to consider. That's the spot where you want your solutions to go through. Okay, so what's a solution? We've seen this analytically. It's just some function. If you have some function that satisfies the differential equation, that's your solution. And then in the geometric side, this is what the integral curves were. So the integral curve was just the graph of some function here. So that's the geometric story. And then the real meat of what it means to be a solution to an initial value problem as in an ODE plus an initial condition, what it really meant analytically was that your solution solved that ordinary differential equation. If it was an initial value problem with an initial condition, it would solve that initial value problem. So you plug it in analytically, you take your derivatives, and you see that it matches. And what that meant geometrically was that that integral curve was tangent at every point to the slope field. That is, the slope field and the tangent to the curve were identical. And indeed, if you specified an initial condition, you would ask of all the possible integral curves, which of the integral curves goes through that point that is represented by the initial condition. And so we have these two sides, the geometric world and the analytic world, that really we've now connected the major concept of both worlds together. They live in parallel.